Alright, let's talk a little bit about coordinate systems and the basics of what we're talking about so that it kind of makes sense. Coordinate systems are not an easy topic, and they are a source of a lot of difficulty, particularly in this class. As you move into other classes, you'll come across the same problems that you're having now, and you will, in time, get better at it. So coordinate systems are important. They can be something as simple as an arbitrary coordinate system like you're using to survey a location, to where you have a grid, you have a X and a Y line, and you simply go so many units in either direction to identify a point. Pretty simple. But when we look at it in terms of mapping and global, it becomes a little more complicated. So we're going to make a bunch of distinctions in terms of how we describe or define what coordinate systems are. And the first one is to say that coordinate systems come in one of two forms. And I'm going to say one of two, one of three, one of five, one of whatever, a bunch of different ways, because we're going to subdivide this out a lot. But at the basic level, it's one of two ways: projected or unprojected. Unprojected coordinate systems deal with the idea of a globe type shape, and from that we use spherical coordinates, in other words, angular degrees of latitude and longitude. That is unprojected or geographic coordinates. That would be what we would refer to as a GCS, geographic coordinate system. Now, rather than carry around globes, we like two-dimensional flat maps. And so we have to convert that roundish object into something flat, and to project that is not an easy task. It requires a lot of work and some math equations, and once we convert that spherical thing into a flat square looking thing, it becomes a projected coordinate system, or a PCS. Here is a nice USGS map, and I want to point out a couple of things. These maps are awesome. This is a topographic map, shows elevation changes along ISO lines. But what's really interesting is the numbers along the side. And if you look at those numbers, look at the top circle, you see where it says 44 degrees 15 minutes by 132 degrees 52 minutes 30 seconds. Those are degrees. Those are geographic coordinates for that intersection of those two lines. Further down the left border, you'll see 4899,000 MN. Those are UTM coordinates. And then down at the bottom, you see 710,000 feet south. Those are state plane coordinates. On an individual USGS map like this, you have the ability to identify the geographic coordinates at locations, the state plane coordinates at locations, or the UTM coordinates at a location. So it is indeed possible to have one location to have three different set of XY coordinates. So here we have this location, this Dottie School. If it's in UTMs, the XY coordinates are 631058.40 by 4885805.77 meters. If it's in a GCS, its XY coordinates would be 103 degrees 21 minutes 43.83 seconds west by 44 degrees 6 minutes 49.26 seconds north. And if it's state plane, it would still have another set of coordinates. So yes, it's possible to have one location with three different set of XY coordinates. This is why the label is important, because if you don't know that it's UTM zone 13, if you don't know it's in a GCS, if you don't know it's in state plane, those numbers don't make sense. So let's talk about coordinate system data. Every feature class stores its XY values based on the specifics of its coordinate system. The coordinate system can be projected or unprojected, as I said earlier. And the feature class has also a label that documents these parameters, and those parameters are what the software uses to interpret those numbers and to properly place things in the GIS. Collectively, we call this the spatial reference. Every data set requires a complete description to properly display. What is the spatial reference? It's a geographic coordinate system or datum. It's the projection if it's in a projected coordinate system. It's the storage units, in other words, what are the units that go along with the XY values, degrees, feet, etc. The domain, the maximum allowable XY values, and the resolution or the precision of the XYs. So let's talk a little more about GCSs, geographic coordinate systems. They measure degrees, angular degrees. Imagine starting in the center of the globe, identifying an axis that runs north-south, and from that you identify a single line or a meridian, and as you move from that line you get some degrees. Thing to remember is that prime meridian is a 0 degrees of longitude. Latitude is changes from north to south angularly from the equator being the 0 line of latitude, and as you move up, positive, down, negative from that. Now, some people have problems remembering longitude and latitude. Remember of it like this. Think of the cold, worst, foul winter weather you can imagine, and how nice it would be to go to, like, say, Florida in the middle of February. How much happier you would be to get away from all the snow and the cold and the slush and the rain. And there was an old slogan, I think it was actually for a beer commercial. It said something about changes in latitude cause changes in attitude. So as you move closer to the equator in the winter, you get happier. And so that change is in latitude because that change would improve your attitude. Does that make sense? Anyway, here's what they are. Practice them, learn them, commit them to memory. Now once we have a measure of longitude and latitude, from those two things we simply can then pinpoint any individual location anywhere on that sphere-shaped object. So what sort of properties go along with our GCS? It's angular degrees, but we need to know a little bit more. We need to know the shape of the thing that we're measuring the degrees on. If you have unprojected data, in other words data that's in a GCS, 1 degree, 110 kilometers. Think about that. It makes it really hard to do accurate work in a GCS. Turns out, when you're measuring these angular degrees, it's not on a perfect sphere. It's actually on an ellipsoid. An ellipsoid is like if you took, for example, a perfect sphere and you sort of sat on top of it, and it equally matched the bottom and the top. So it's still a mathematically perfect shape, okay? It's just not round. It's loosely defined as roundish. But we can still find a center, and from a center we can measure around it at the equator or at the central axis, and we can measure up and down from the equator area to the north or south poles. So we can calculate an angular degree measure of longitude and latitude on this ellipsoid. But turns out the Earth, conveniently, is not an ellipsoid. It's actually something that vaguely resembles a pear that someone kicked and rolled down a flight of stairs. It's very irregularly shaped. And we model the Earth as something we call the geoid. The geoid is not a perfect ellipsoid, and it is not a topographic surface either. The geoid is a theoretical surface that is defined by measures of gravity. Some describe it as the mean ocean surface of the Earth. And what we're talking about is if you can imagine the Earth kind of quit spinning, if you will, and was at rest. where would that water balance out to? Turns out some parts of the Earth are more dense than others, and so they have a stronger gravitational pull. And so in some of those locations, the water surface would be higher, and other locations it would be lower. Once you figure out from a gravity standpoint where this is, that gives us this shape. And so it is in some ways similar to the surface of the Earth, but it's not the same thing. It's a gravitationally measured surface of the Earth, and we call it the geoid. And that is what we map off of. Problem is, it's not a perfect surface. And so all that fancy math that we do to calculate angular degrees and stuff, it just doesn't work very well on a geoid. So we do something called creating a datum. And basically what we do is we take an ellipsoid that is the closest approximation to the geoid that we can find. And then if you can imagine grabbing that center point, that 0, 0, 0, right middle of the planet kind of a spot in that ellipsoid, and we gently move it around up and down, side to side, front and back, until as much of that ellipsoid lines up with as much of that geoid as we can get at the place that we're interested in. Now, if we're doing something locally, like say just the US, we're only concerned with how that part of the geoid lines up with that part of the ellipsoid. We don't give, two hoots about what it does everywhere else. We can also do a geocentric or a world-centered datum. This is one where we try to fit it the best we can for everywhere, and that is another type. Ultimately, once we make these shifts and we figure out where we have to position stuff, it allows us to go down this road of creating a datum. To create a datum, we simply need to know the length of the x and the y-axis of the ellipsoid, and that adjustment of fit, or in other words, how we had to move it around to make it line up. So what is the definition of a datum? It is a particular ellipsoid with a major and minor axis, major being the long axis, minor being the short axis. And the adjustment of fit to the center, in other words, that translation of center, how you had to move it around to get the ellipsoid to line up, the spheroid, to line up with a geoid. And ultimately, that is what creates a datum. That's how the datum is defined. And from that datum, we can then calculate geographic coordinates. Most common datums in North America: NAD 27, NAD 83, NAD 83 Harn, and WGS 84. Every projection that you have, every projected coordinate system that exists, is based on a geographic coordinate system. You can't have a projected coordinate system unless you have a GCS. The GCS is the basis from which the projection calculates. Every GCS that exists is based on a datum. From an individual datum, there could be multiple geographic coordinate systems. From an individual GCS, there could be multiple projected coordinate systems. But for any given projected coordinate system, there's only one GCS and only one datum. Think of it like a branching tree. The datum is the stump. The first branches are the GCSs, and the leaves are the projections. If you have projections based on one datum, they're going to be offset from another. The amount of offset depends on which projections and whether they're geocentric or local. Typically 0 to 300 meters. Sometimes things line up perfectly. Sometimes it's off. Sometimes it's off a lot.